Let's revise a bit on Bohr's atomic model. Electron at excited state is unstable and will fall back to lower energy level. During this transition, it will release energy, and the energy released is in the form of light and it is called photon. Since photon is a type of wave, the energy transmitted through the electron transition can also be presented in terms of wavelength and frequency. The energy of the photon is given by the formula delta E equals to hv, where h is Planck constant, which is 6.63 times 10 to the power of negative 34 joule second, and v is the frequency of the photon. Since frequency is a positive value, delta E used in the formula is without its negative sign. Since wavelength is inversely proportional to frequency, the equation can also be expressed in this form, where c is the speed of light with the value of 3.0 times 10 to the power of negative 8 meter per second. Now, by using the Bohr's equation that we have learned earlier, we can derive a new set of equations that can relate between the lambda of the photon and the transition made by the electron that produced the proton. Remember the Bohr's equation to calculate energy emitted by the falling electron? Now combine with the formula of delta E that we have just learned, it will produce this equation. Now taking this combined equation, we can simplify the formula by taking all the constant at one side. That is, our Rydberg constant, Planck constant, and speed of light is grouped at the right hand side of the equation, leaving lambda at the left hand. Now let's substitute this group of constant with a single constant. This new constant have the value of 1.09 times 10 to the power of negative 7 per meter. This new constant, however, is still known as Rydberg constant. This new simplified equation will then have to go for a slight modification. Remember that the photon is produced when the electron fell from higher level to lower level. This will mean that its end initial will be of higher value compared to its end final. If we substitute this value in the formula, it will give us negative value for 1 over lambda. Since lambda is a measurement for wavelength, it should not have negative values. To make sure lambda will always have positive value, then we have to alter the usage of end initial and end final to N1 and N2 instead. The value of N1 should always be less than N2. Since the falling of electron involves transition from higher level to lower level, we should set N2, which has the higher value, as the level where the electron initially is, while N1 with lower value should always be the level where the electron falls to. This way, the value of lambda should always be positive. Let's do one example. Calculate lambda for the photon emitted by the electron that falls from n equals to 5 to n equals to 1. To solve this, since electron falls from n equals to 5 to n equals to 1, let's replace N2 with 5, which is the higher value, and replace N1 with 1, which is the lower value, to the formula. Now the lambda for the photon will be 9.52 times 10 to the power of 6 meter.